Let's take a look now at section 9.9, representation of functions by power series. We've seen that we can define a function using a power series. We can say f of x equals the sum as n goes from 0 to infinity of some terms, which look like a sub n x to the n. But is that function another function that we know? If I say f of x is equal to the sum as n goes from 0 to infinity of x to the power n over n factorial. Okay, that is a power series, but I've just defined this function using a power series. Is this a function that I already know? Is it the sine of x? Is it the arctangent of x? Is it some other function that we know? Is this a function already known by another name? The answer is usually no. If we make up our own function and just say, okay, this is whatever we choose for it to be, it's probably not some other function. It's probably just something that we defined arbitrarily. But there are going to be some functions that can be designated by another more familiar name. In the last section of this chapter, we'll see how that's done for some very key functions in algebra, trigonometry, and calculus. But for right now, let's start off with the simplest case. Let's talk about what we get when we look at series that look like a geometric series. So recall, and this was from the very beginning of chapter 9, 9.3, I believe. We were talking about the geometric series. And the geometric series is the one that looks like this. N goes from 0 to infinity of a times r to the power n. This is equal to a over 1 minus r whenever r in absolute value is less than 1. And it converges whenever r in absolute value is greater than or equal to 1. Well, notice that this is a constant, and that's a constant to a power. That looks like a power series. This looks like a constant times x to a power. And in fact, if we were to say, oh, let's treat this as a variable, if we take the series, n goes from 0 to infinity of, here I'll just use a as the number 1. So here I'll just say x to the power n. That's going to converge to 1 over 1 minus that x. But again, it won't converge always. It'll only converge whenever r is less than 1 in absolute value. Oh, that'll be our radius of convergence. But we'll diverge diverges whenever the absolute value of r is greater than or equal to 1. Okay, so here we have, in fact, a power series. It turns out that the power series, the sum as n goes from 0 to infinity of x to the power n is equal to 1 over 1 minus x. So if ever you have this power series, you can treat it as it's a power series, or as long as you have a value that's between minus 1 and 1, excluding minus 1 and 1, as long as you're in the interval of convergence, then this series can also be treated as this familiar function, 1 over 1 minus x. Surprisingly, this one function will be sufficient to give us quite a lot of other functions. Now, it won't give us everything, but it'll give us a good starting point to see that traditional functions can be defined as power series. Once we're comfortable with that fact, we'll go on to see ones that are not quite related to this one. But we're going to start with this. All right, so let's say I wanted to take this function and write it as a power series. Well, I'd write it this way. So here, if I call f of x equal to this power series, that's the same as calling f of x equal to 1 over 1 minus x. But if this is a function, I should be able to do the same things that I usually do with functions. In particular, I should be able to plug in different things. So here, let's say I wanted to find a power series for f of x is equal to 1 over 1 plus x. Now, that's different than this one. Well, yeah, but really the only way that's different is that sign there. And in fact, I could write it with a minus. I could say, well, and here's an example. Here I could say, well, okay, 1 over 1 plus x, that's really the same as 1 over 1 minus a negative x. But notice, that's the same as this with, instead of an x, I have a minus x. Well, then shouldn't it be the same series, but instead of with an x, we have a minus x? Well, sure. So here, this is going to equal to the sum, as n goes from 0 to infinity, of minus x to the power of n. Or we may be more, we may have a simpler time writing it this way. We can separate this. After all, minus x is minus 1 times x. So I can write this as minus 1 to the power n times x to the power n. And that way it looks more like an alternating series. This will be convenient for other things later. Notice that just like with any function, if I want to replace that x with a minus x, or I want to replace that x with a 2x, if I want to replace that x with anything, all that's happening is I'm replacing this x with that exact same thing. So f of 1/3, I replace that with a third. F of 9, I'd replace that with 9. F of negative x, okay, I'll replace that with a negative x, just like that. So in fact, there's our power series. 1 over 1 plus x is the same as the sum as n goes from 0 to infinity of minus 1 to the power n over x to the n. But again, this must be whenever minus x in absolute value is less than 1. And here I wrote that as r, it should be x. Because here I've changed r to x, r to x. Here I still have a radius of convergence of 1. Here note, I still need for this negative x, this thing that we're calling r, we still need for the absolute value of that negative x, which is really the absolute value of x, because the negative would go away, we still need that to be less than 1. So note that even when you are changing your interval of, even when you're changing your function, you still have to consider its interval of convergence. Okay? So now we take this and say, okay, well, let's consider something else that's related. Let's find a power series for f of x is equal to 1 over 1 plus x squared. Well, that's basically this one, but instead of with an x, I have an x squared. Oh, okay. So here, let me go ahead and call this a different name. I called the last one f. Let's call this one g, just for the sake of my notation here. All right, so I want to find g of x. Well, notice g of x is the same as f of x, but instead of an x here, I have an x squared. Okay, so that's going to be f of x squared. Right? This g of x is the same as this f of x, but with, instead of an x here, I replace that x with an x squared. Okay, so g of x is just what happens when you take f of x and replace x with x squared. Oh, but here, this was f of x. So now let me take that x and replace it with an x squared. That's going to be the sum, as n goes from 0 to infinity, of minus 1 to the power n. And then that's going to be what? X squared to the power n, which is the sum as n goes from 0 to infinity of minus 1 to the n of, well, here, something that's got a power that's being raised to another power. We can go ahead and multiply those powers together to give us x to the power 2n. And there's a power series. As long as we have one basic power series, we can perform substitutions to give us a new power series. Notice again that we need our expression here, the thing that we substituted in, we need that to be in absolute value less than 1. So here note that we still consider an interval of convergence, namely we need the absolute value of x squared to be less than 1, and which is really just the same as saying the absolute value of x is less than 1. Essentially what we're saying is, okay, all of these series were made with an initial series that had this interval of convergence. We want our x to be less than 1. And if you notice, if this only exists between -1 and 1, well, then anything that we build out of it would also only exist from -1 to 1. All right? Okay, so now we have a power series for 1 over 1 minus x. That was the original one that came from the geometric series. We use that to build the power series for 1 over 1 plus x. And then we use that to build the power series for 1 over 1 plus x squared. And in fact, there it is. So now, go ahead and try this. Let me say, oh, okay, so we're just going to substitute something in. Well, let's see. Find the power series. For, I'll call it h of x is equal to the arctangent of x. At this point, you think, okay, I must have skipped something. That can't possibly be right. Well, no. Actually, if you look back at the last two examples that we saw, from those, you should have all the information you need to find this one. So give it a try. Pause the video, and whenever you're done, go ahead and unpause, and we'll go through it together. All right. Here, note that the arctangent of x is the integral of 1 over 1 plus x squared. Here, recall that if you take arctangent of x, that's equal to the integral of 1 over 1 plus x squared dx. Plus a constant of integration, but this is one antiderivative of that. Okay, but then I know the power series of this one. That's going to equal to the integral of the sum as n goes from 0 to infinity. Our last example showed us its power series was -1 to the n times x to the 2n, -1 to the n times x to the 2n dx, like that. Okay. Now, I mentioned in a previous section this change of limits, saying, okay, that's a limit, that's a limit. Switching those is not a trivial thing, but as long as we stay in the interval of convergence, that's perfectly valid. Basically, as long as this converges to something, which we saw already is between -1 and 1, here, the interval of convergence, is between -1 and 1. So as long as you're staying in there, this is a perfectly valid procedure. That's, instead of saying the integral of this sum, we're going to take the sum of this integral. Okay. Notice that's a constant with respect to x, right? That's just -1 or +1, which means I don't even have to worry about that one. I can just write this as the sum as n goes from 0 to infinity of -1 to the power n times the integral of x to the 2n dx. Right? That's a constant with respect to x. There's no x there, so it can be brought out thanks to the linearity of our integral. But now, that's just a regular old x to a power. And I can take an integral by adding 1 to that power and then dividing by the new power. So this will give me the sum as n goes from 0 to infinity of -1 to the power n times x to the power 2n. We're adding 1 to that power, so that's now 2n plus 1. And then we're dividing by that new power. Just like that. Now you say, don't I have a constant of integration? Don't you have a plus c whenever you have an integral? Well, that's true. And of course, if that's plus a constant, that can't possibly be right, because here there should only be one power series for this one. Here I end up with a lot of power series. Oh, okay, so how do I know what that c is? Right here I have a lot of power series that this could be. Well, not really. I mean, yeah, there's a bunch of power series that this could be, but really the only difference is that c. So now let's go ahead and plug in a nice convenient number. After all, this function is centered at 0. Right? This isn't x minus 5 or x minus 12. It's x minus 0. So that's centered at 0. So let's plug in 0. if we plug in 0, that's going to give us that the arctangent of 0 is equal to the sum as n goes from 0 to infinity of minus 1 to the power n times 0 to the power 2n plus 1 over 2n plus 1 plus a constant. But notice that's just 0 plus 0 plus 0 plus 0 plus 0 plus 0 forever. Oh, well, that's got to be 0. Okay, so that whole thing's got to be 0. And here, the arctangent of 0, we know that's 0 as well. So here, C must equal to 0. So C must equal to 0. Okay. All we did was we took our power series from before. Arctangent of x is equal to that power series plus C. Okay, now plug in 0. Okay, well then, when you plug in 0, that whole thing becomes 0. So all you're getting is that the arctangent of 0 is equal to that constant. But since the arctangent of 0 is 0, then that means that constant must also be 0. Thus, that tells us that that C should just be 0, and that's the one and only power series that we want. So that gives us that the arctangent of x is equal to the sum as n goes from 0 to infinity of minus 1 to the power n times x to the power 2n plus 1 over 2n plus 1. Or at least it is, as long as you're between minus 1 and 1. And that's our power series. Now, every series that we've seen so far has been centered at 0. All right? The arctangent, 1 over 1 plus x, 1 over 1 minus x, 1 over 1 plus x squared. None of them have been x minus c. They've all just been x, which means the center is 0. Let's take a look at a couple of examples where our center is somewhere else. So let's consider the series for the function f of x equals 3 over 2x minus 1. And now what we want to do is we want to find the power series centered at c equals to 2 of that function there. All right, well, if our function is centered at 2, what that means is that that x shouldn't be an x. It should be an x minus 2. Okay, well, that's not too bad to do. I can rewrite this, and all of these, everything that we're about to do, there's going to be no calculus until the very end. It's all algebraic. All we want to do is we want to write this in the following pattern. We're going to want a over 1 minus x minus 2. Something like this. Here, it's okay if we have a constant. So here I'll just say, I don't know, let's say b. So here, that x minus 2 guarantees that my center is at 2. Having a over 1 minus something, that guarantees that it'll be a geometric series. So what we need to do is we need to take this and write it as a number over 1. That 1 is non-negotiable. It has to be a 1. Number over 1 minus some constant times x minus our center. Okay, so all we're doing is we're manipulating this until it looks something like that. All right, well, I don't want an x. I want an x minus 2. So let me write that this way. I'm going to leave my 3 alone for now. I'm going to write this as 2 times x minus 2. Right, that way that looks like that. But now notice my constant has to change. This is 2x. All right, that's what it's supposed to be. That's minus 4. Oh, it's not supposed to be minus 4. It's supposed to be minus 1. Okay, so let me add 3 to balance that out. I shouldn't change what this says. I should only change the way it looks. Okay. Now, okay, I note that I want this part on the end and I want a 1 in the front. So here, let me switch these around. Let's write that as 3 over 3 plus 2 times x minus 2. Okay. Well, yeah, but that's not a plus. That's supposed to be a minus. Oh, okay, well, that's not too bad. I can just write that as 3 over 3 minus a negative 2x minus 2. Notice, none of this has changed. The numerator is still 3. The denominator that would be a positive 2x, which is what I was supposed to have. And this would be positive 2 times negative 2. Well, it's negative 4, but then that extra 3 brings us back to negative 1. Nothing about this has changed other than how it's structured. Okay, we're almost there. Number over 1 minus that thing. Oh, but that should be a 1. Okay, so let's divide top and bottom by the number 3. Divide by 3, divide by 3, divide by 3. So that'll give us 1 over 1 minus 2/3 times x minus 2, like that. All right, and there we go. This is now in the form of the result of a converging geometric series, a over 1 minus r. So here I get that a, so we can write this result as a geometric series with a equal to 1, that's my numerator, and r equal to the stuff that I'm subtracting away from the number 1. So r is equal to 2/3 times x minus 2. And so f of x can be written either as 3 over 2x minus 1, or as a power series centered at 2, it can be written as the sum, as n goes from 0 to infinity, of a, which is just the number 1, I'm not going to bother to write it, times r, which is 2/3 times x minus 2 to the power n. A times r to the n. And that's our power series. The next example that we're going to look at, that was an example here. The next example we want to look at is, note that this is a sum. Well, what if I took this sum and another sum and combined them? Well, we could add two sums together. And the nice thing about adding two sums together is that they just become one big sum. All right, if I have 2 plus 3 and I add 4 plus 5, I can just write that as one big sum, 2 plus 3 plus 4 plus 5. This may have an infinite number of terms, but it works the same way. I'm still going to add together all of them into one big sum. So here, we're going to start off, and we're going to do this one in stages. This was kind of a big problem. So here we want to find the power series centered at 0. At c equals to 0, of f of x equals to 3x minus 8 over 3x squared plus 5x minus 2. Right. Okay, well that looks very, very, very unpleasant. Well, yeah, that denominator is a quadratic. And it's not like constant minus x or constant minus x squared where we can get away with a quick substitution. Well, yeah, but the reason that looks like that is because that denominator is, well, it's really unpleasant looking, right? Well, it doesn't have to be. I can factor that. That denominator factors as, let's see, 3x, and then that's an x, and that'll be minus 1 and 2. Right? Okay, well, that factors out that way. Well, each of those denominators is kind of nice, but oh well, I don't have each of them on their own. I have them together. Okay, so split them on their own. Here, we can write this as 3x minus 1, x minus 2. We can split them using partial fractions. So take a minute and try that. We're not going to go all the way through to finding a power series. I'm going to have you try this in stages. So the first thing I want you to do is go ahead and split this as a partial fraction. Once you're done, go ahead and unpause the video and we'll continue the problem. Okay, so let's go ahead and split this as partial fractions. All right, remember how that works. We're going to take 3x minus 8 over 3x minus 1 times x plus 2 is equal to a over 3x minus 1 plus b over x plus 2. All right? Here we have distinct linear numerators, which means my numerators are just going to be constants. Each of these factors will get a chance to be a denominator, and the numerators will be constants. Here we're going to multiply everything by the common denominator, namely 3x minus 1 and x plus 2. And many things will now go away. So now we're left with something much simpler. We're left with 3x minus 8, since that entire denominator is gone, is equal to a times x and a times 2. Okay, so ax plus 2a. And here we're left with, since those are gone, b times 3x is 3bx, and b times negative 1 is negative b. All right, well then that means that if I take that a and I add that 3b, that must give me the coefficient of x. So this is going to give me a plus 3b is equal to 3. And then adding the constant with the other constant should give me that constant. So 2a minus b is equal to negative 8. All right, now that's just a nice system of equations. Let me triple this bottom line. So here's my system. I can write that now as a plus 3b equals to 3. If I triple this bottom line, that's going to give me 6a. That's going to give me negative 3b. And that'll give me negative 24. So now if I add the two lines here, that's going to give me 7a. That's going to go away. And that's going to give me negative 21. And so I can divide both sides by 7. And I get a is equal to negative 3. All right, awesome. A is equal to negative 3. Over here, we saw that a plus 3b is equal to 3. Okay, so a plus 3b is equal to 3. Oh, but we know a is equal to negative 3. So that gives us that negative 3 plus 3b is equal to 3. We can add that 3 over to the other side. That'll give us 3b is equal to 6. And then divide both sides by 3, which gets us our result. Okay? So we found our a and our b, and that tells us that here, this a should be the number negative 3, and that b should be the number positive 2. Okay? So I'm going to switch over to another page here. And that's going to give us that f of x, which is equal to 3x minus 8 over 3x squared plus 5x minus 2 is equal to negative 3 over 3x minus 1 plus 2 over x minus 2. Okay, just like that. So all I've done is I've said, okay, I know I split that up this way, but now I know my a and b, so I fill in my a and my b. All right. And that should be a plus right there, shouldn't it? Okay, so now each of these looks like something that we've been working with. We can find the power series of this one, and we can find the power series of this one by treating them both as the results of a geometric series. So that's the next part of the problem. Go ahead and pause the video and try to find the geometric series of this one, and separately find the geometric series of this one. Once you're done, go ahead and unpause and we'll do it together. So I want to write these as a number over 1 minus another number. Okay, so let me just go straight down here. Well, first of all, I notice I have a negative here. So let me multiply the top and bottom by -1. So now that's a +3. This -1 is now a +1, and that +3 is now a -3. And you know what? We're done with that one, because that's a over 1 minus that whole thing is r. So this one's nice and straightforward. This other one's going to take just a little bit of effort. Notice our center that we want is 0. So here we're not looking for x minus anything else other than just x. All right? X minus 0 is just x. Here, let me go ahead and write this one as 2 over. Well, I know I want the constant in the front. So let me write this as 2 plus x. But again, I know I want to be subtracting something here. So instead of writing it as 2 plus x, I'll write it as 2 minus a negative x. Yeah? These still say the same thing, but now I have a number over 1 minus a number. Oh, well, that's not 1 yet. Okay, so let's fix that. Let's go and divide both the top and the bottom by 2. And the reason I'm dividing by 2 is this needs to become a 1. We don't really care about those. That needs to be 1. So here we can write this as 3 over 1 minus 3x plus 1 over 1 minus, and in here we'll write this as negative 1/2 x. All right, minus negative 1/2 x. Oh, but now both of those are the results of geometric series. This one, I have an a, which is just the number 3, and r, which is 3x. Over here, I have an a, which is the number 1, my numerator, and an r, which is negative 1/2 x. So that means my power series is the sum, as n goes from 0 to infinity, of a times r to the n, plus the sum as n goes from 0 to infinity. For this one is going to be a, which here we'll just leave as the number 1, times r to the power n. Just like that. But since both of these are sums, we can add the terms together. So we can write this as the sum as n goes from 0 to infinity of 3 times 3x to the power n plus negative 1/2 x also to the power n. The sum of these sums, we just reorder the terms. Say, take the first one of this one and the first one of this one, that's the first term of this sum. The second term of this sum and the second term of this sum give us together the second term of this sum. Basically, we're saying it's one big addition, so let's just do it whatever order we like. Okay, but now I can rewrite this a bunch of ways. Here, let me just stick to something reasonably simple. I'm going to go ahead and split this as 3 to the power n and x to the power n. Over here, I'm going to split this as minus 1/2 to the power n. And I'll have x to the power n there. But now I notice x to the power n is common, so I can write this as the sum as n goes from 0 to infinity of 3 times 3 to the power n times negative 1/2 to the power n of x to the power n. Like this. Oh, sorry, that should be a plus right there. And finally, here, I suppose these have the same base, so let me add their powers. And so this will give me, in the end, sum as n goes from 0 to infinity of 3 to the power n plus 1 plus negative 1/2 to the power n. Those are my coefficients of x to the power n. And this is a power series that represents that function up there. Now, we are done making the power series, but we do have to be careful. Remember, this is only true if you're in the interval of convergence of this series. Basically, if this converges, it equals to that. If this doesn't converge, well, it doesn't equal to anything. So the last step here is we want to find the interval of convergence. You say, well, that looks really, really unpleasant. I have to find the interval of convergence of that thing. Well, you could, but a simpler thing to do is come back up here. Find the interval of convergence of each of these. Because if this one exists for all real numbers, but this one only exists whenever x is between -1 and 1, well then it doesn't matter if this one exists for all real numbers. If they don't both exist, then you couldn't have done this in the first place. Both of these have to exist for you to be able to add them together. You can't add a number to something that doesn't exist. So here, what we want to do is we want to find our intervals of convergence, and in the end say, where do they overlap? We want to find the overlap. We want to find the intersection of the two intervals. So that'll be the last stage of this problem. Go ahead and give this a try. You're going to find the interval of convergence of each of these. It shouldn't take very much because they are geometric. And once you find them, find the intersection, find the overlap, and that'll tell you the interval of convergence of your final result. Pause the video, and whenever you're done, go ahead and unpause, and we'll go through it together. All right, so this one's not too bad because it's geometric. We know that a geometric series will converge as long as r is less than 1 in absolute value. So here we're going to take 3x in absolute value to be less than 1. Oh, but here 3 is already positive, so we can take it out of the absolute value. So that's 3 times the absolute value of x is less than 1. And if I divide both sides by 3, I get x must equal to, absolute value of x must be less than a third. Okay, so then that means my interval of convergence is, here my center is 0, right? That was from the very beginning. All of our functions are centered at 0. So then from 0, I want to go 1/3 of a unit in either direction. So from -1/3 to 1/3. This one over here works pretty much the same way. I want to find my interval of convergence. Well, that means I need that absolute value of -1/2 x, that should be less than 1. Now, if I'm taking the absolute value of this, that just is 1/2 times the absolute value of x is less than 1. Those two mean the same thing. But now I can go ahead and multiply both sides by, let's see, what do I have, by 2. And that'll get us the absolute value of x is less than 2. And again, since we're centered at 0, that means our interval of convergence is everything between -2 and 2. So that means that the interval of convergence of our series at the end, which has interval of convergence, and here what we want to do is we want to take where these overlap, -1/3, 1/3 intersect with -2 to 2. Right? Here, if you just draw a picture of that, you have your number line. Here's 0. -2 to 2 is over here. -1/3 to 1/3 is here. And the overlap is just, well, from -1/3 to 1/3. One is inside the other. So the overlap is the smallest of the two. So that's going to give us -1/3 to 1/3. So here, this function is exactly the same as this power series, but only if you're in the interval between -1/3 and 1/3. If you're not, well, then this power series does not converge, so it's not equal to anything. It's not equal to this or anything else. And there's our result. Okay. All right, and that brings us to the end of the section. In this section, we've seen how to use the basic geometric series to create other series by either manipulating that one or by combining several of them. However, we still haven't seen generically how to do this. We've seen what happens if you have either a power series that's geometric in nature or if you have one that's related to one of those. In the last section of the chapter, we'll see how to go through and look at this generically. In other words, how do I represent any function as a power series? All right? But for this section, we are done. So the assignment for today, let's have you try for an assignment 7 through 23 odd. And that should suffice. So if you have any questions, please make a note of them and reach out to me and let me know. I hope you all have a nice day.